What's up everybody, I'm Jason and welcome back to the channel. So in the last two videos I talked about compression methods and the compression options that are available on the EOS R5 and the R5C. And in keeping with what I've done for the last several videos of having two videos talking about specific details on either the R5 or the R5C and then a general discussion on that topic, this is going to be the general discussion on compression methods for the cameras as things kind of relate together. Now, I do have to be upfront about something. This is going to be a long video, and I have cut out a significant section talking about compression, raw compression specifically, that I've realized in doing the editing for this that it's just going to be too long and too much in one video to really cover everything that I want to cover when talking about raw compression. So I am going to cover a couple of things in this video. Now, as all of my videos, including the long and short ones, there are chapter markers that are available that you can use to jump to a section if you're interested in the content of that section. If not, feel free to watch the video or feel free to jump around to whatever section you find that you are most interested in. So I'm going to be talking a little bit about objectively comparing compression methods. I'm going to be talking about some observed differences between the EOS R5 and R5C when it comes to the video compression and how that can sow some confusion in what's going on if you are not completely familiar with the entire situation. And then I'm going to talk a little bit about raw video as it is implemented by Canon on their cameras. So let's start by talking about comparing compression methods objectively. And what I mean by this is, not looking at a video and subjectively saying, oh, I think there's more noise in the shadows here, or that this is cleaner, or this is blocky, or whatever. That's certainly a valid way to go about doing it. In fact, that's pretty much the only real functional way we have to go about evaluating different compression methods, at least as it comes out of the camera. So the objectively comparing video quality is one of those things that's, well, best described as being difficult at best. Now, I'm going to make the argument that objective comparisons, being able to feed something into a computer and have the computer tell us the relative quality is actually really important in the whole sort of choosing of codecs, choosing of processing, etc. And the reason that I make this argument is simply because when it comes to subjectively looking at video quality or video or even still image quality, we're going to prioritize things that we are either familiar with or that we are especially sensitive to or that have bit us in a previous project, and possibly to the detriment of prioritizing or seeing things that maybe we really need to see. So while this has nothing to do with video or video compression, an example of this could be, if we're doing lens reviews and I'm subjectively talking about chromatic aberration. I'm, in my experience, not overly sensitive to it. I would prefer it not to be there, obviously, but my vision, my whatever, my experience, etc., I just don't notice it. It's not the first thing I go looking for. It's not the thing that jumps out at me. So if I'm talking subjectively about a lens, quality or whatever, and I'm saying that the chromatic aberration's fine, then somebody else could look at it and say, dude, what are you smoking? That's horrible. Conversely, if I have an objective measure, I feed this into some software. If software says there's 3 pixels of chromatic aberration, I can talk about that, and you can make the call based on how important it is to you. And I think the same thing's really important when it comes to talking about video. So when we're talking about codecs and codec choices and so forth, you're going to have different artifacts. Low bitrate AVC or HEVC has a tendency to macro block. Different raw codecs can have different impacts in the way they render, say, shadows or so on and so forth. And how much of an issue this is going to be for us is it's going to vary based heavily on, what it is that we actually have been bit by in the past and what it is we're sensitive to. So I may be really looking at facial details or something, and somebody else is going to be heavily distracted by the fact that the background in the shadows is incredibly noisy, something to that effect. Ultimately, what this means is that I might say that bitrate X is more than enough bitrate for your content, and somebody else could look at that and say, dude, what are you smoking? Bitrate X is nowhere near high enough, and alternatively, you can have people who are going to look at the same thing and say, that's way higher than it needs to be, you can drop it lower. Compounding matters, of course, is the fact that we're talking about compression. Compression is entirely dependent on content and, in fact, implementation. So if you are familiar with the whole, if you were into gaming or just paying attention to video compression on computers, one of the biggest things that came when NVIDIA released the GTX 2000 or the RTX 2000 series video cards was massively improved quality for their hardware video compression, so AVC and HEVC in the NVENC compression system, compared to their predecessor cards. You can't just say something like, well, it's HEVC or AVC, and you know what, there's a perfectly good tangent here that I probably should talk about. There is an implementation dependency in this. So alternatively, you can't just take, while AVC, HEVC define exactly how video needs to be compressed. It defines exactly what algorithms need to be used. The whole process is incredibly well defined. What it doesn't necessarily define is how capable the hardware that you have is at producing that content. So when we're talking about cameras, obviously we're talking about real-time compression. The camera cannot post-process compress something. It has to be able to do it in time to make the next frame work, in time for the next frame to be read out. What this means, and with the whole thing with HEVC, is that, or AVC, or any of these compression algorithms, is that there's going to be a different amount of mathematical capability that can be applied in the compression process to in real time, depending on the hardware and depending on the capabilities of the hardware. So different, even real-time compressors are not necessarily going to be forced to only use a certain subset of the processing that can be done. They can, if you have a more capable piece of hardware, it could potentially do more of the kind of processing that would normally, or that would be done maybe in post. So if you're familiar with, for example, X264, X265, or even Adobe Media Encoder, where you have different options for the encode speed. You can do like very slow, medium, fast, very fast, etc. Each of those settings is in fact changing how much of the processing capabilities or how much processing is being done to find an optimal way to compress the individual frames. So it's also not necessarily possible to say, without a whole lot more information about what exactly is being done, to say, well, okay, fine, I can't necessarily compare RAW in camera to MP4 in camera because I can't record both of them of the exact same scene. So I'll record RAW, and then I will take that and I will feed that into something like FFmpeg or Adobe Media Encoder, and then recompress that into an MP4 the same way the camera would do it, because remember, this is what we would need to know to compare these out of the camera, and then compare the files using a comparative, an objective comparative program such as Netflix's VMAF. That just doesn't work because we just don't know what the camera is capable of doing for all of which of the options and methods the camera implements versus what would be implemented in software. So this whole thing of not being able to objectively compare this stuff does make talking about compression and image quality somewhat more challenging in a, well, objective sense. So something to keep in mind in the whole thing about when people start talking about image quality. Tools like PSNR, SSIM, and VMAF are great at generational things, but they need identical frames to compare to. So you can't take something where, you record a clip of a scene and then you record another clip of the scene with different settings and then compare the two. It doesn't work that way. So I want to talk briefly about the differences between the R5 and the R5C. Now, at least when it comes to compression, codec, etc. There are terminology differences. I've touched on some of the terminology differences in the video that I produced, the two videos on compression, but there are some things that I'm not sure I was entirely clear on, in part because of the way that whole project got shot. Canon uses different terminology depending on which groups built the camera. If you are using a camera from the still photo group, so that's the EOS R5 or R3 or R6 or whatever, those hybrid cameras, there's one set of terminology and standards that that group uses. If you are using a camera from the cinema group, or running the cinema EOS OS, such as the R5C or the C70, C200, 300, etc., that uses a completely different, I won't say completely, but a different set of terminology and standards. And so this is one place where, especially when it comes to talking about RAW and RAW video, that things can potentially become confusing. So the photo group has chosen to call the two RAW compression levels on the R5 RAW and RAW Lite. And if you look at the specs for the cinema EOS cameras, such as the R5C, you'll find that they say that everything is shot in Canon's Cinema Raw Lite codec, and then you have three quality levels: HQ, high quality, ST, standard quality, and LT, or light. They're all the same. There is no, the R5 does not implement a RAW and then RAW Lite. Both of the RAW compression options in the R5C or the R5 are RAW, Canon Cinema Raw Lite. The difference between the two is essentially the nomenclature. RAW on the R5 corresponds to ST quality RAW Lite on the R5C, and RAW Lite on the R5 corresponds to Lite or LT quality on the R5C. But the underlying codec is RAW Lite, Cinema Raw Lite across the board. Now, that said, while the terminology is different, but the underlying codecs are the same, there are actually differences in the bit rates that Canon uses that the two divisions use. So when it comes to shooting in RAW, even though the R5 and R5C basically are doing about the same thing, they're not using the same bit rates, or at least they're not targeting the same bit rates. So the R5 targets a higher bit rate for RAW video than the R5C does. I have no idea why. This seems like one of those places where you would expect the cinema camera to target a higher bit rate than the still camera. But then again, maybe on the same token, the still team was thinking about the fact that you might extract still images from raw video, and therefore they wanted to target higher bit rates so that you had better quality stills or something like that. But that is a notable difference between the two. Conversely, if you were shooting in AVC or HEVC, so on the R5, this would be MP4 in either IPB All-I or IPB Lite. The cinema cameras in either XF-AVC or MP4 actually target higher bit rates typically than the R5 does for those same settings. So the next thing I want to talk about briefly is movie crop mode on the R5 and RAW and HDMI Raw. Now, when I talked about the R5 and the compression options, I didn't actually talk about HDMI Raw. And the reason that this happened is largely how this whole group of videos sort of worked or developed for me. Initially, I had intended to just talk about the three rows in the video compression or the movie record size menu on the R5. So there was going to be a video on resolution, there was going to be a video on frame rate, and there was going to be a video on the compression options. On the R5, HDMI Raw is not in that menu. It is a completely separate setting. In the process of doing this, I realized that I would also be able to cover that the R5C basically has all of the same settings, and that it would be probably a good idea to cover them in the same time or same fashion. So after shooting and setting up and shooting all of the R5 videos, I went back and shot all of the videos for the R5C. Now in the R5C, HDMI Raw is actually a part of the compression method selection. So it's completely different in that respect from the R5, which is why I didn't include it in the R5, and that was what I was alluding to just a second ago when I was talking about how I put this together. It was not quite as planned out as maybe I should have had it. In any event, On the R5, there is one notable deficiency, you could call it, compared to the R5C, and that is the lack of support for RAW recording or internal RAW recording when you're in movie crop mode. The camera is capable of doing it. So you can shoot stills in RAW in APS-C sensor size. That works fine. The sensor processor, the only real difference between the R5 and the R5C is that the sensor is not mounted in a stabilizer package on the R5C, and the fundamental software that's running the camera is different. But the hardware, the processor in the camera, the sensor in the camera, it's exactly the same capabilities between the two cameras. So the R5C can shoot RAW internal recording in all of the crop modes. So you can shoot it 8K RAW in full frame, you can shoot 6K RAW in Super 35, and you can shoot 5.7K RAW in Super 35, and you can shoot 3K RAW in Super 16. The R5C has no problem doing it. The R5, for whatever reason, will not do RAW recording in movie crop mode. I don't get it. However, if you are shooting HDMI RAW, so you are using an Atomos Ninja or Ninja 5 or Ninja 5 Plus recorder. You need the Ninja 5 Plus to do 8K, but the Ninja 5 can do 6K. The camera will output RAW from movie crop mode over the HDMI terminal to your external recorder. I have no idea why Canon didn't do the smaller RAW format internally. It certainly would allow the camera should be able to support it. I know people would probably argue that it's for product differentiation, but then if you're going to product differentiate it, why allow RAW to be recorded externally? I don't know. I don't get it. Okay, so with that out of the way, let's get to talking about RAW video in the Canon world. It's complicated, and Canon hasn't done an awful lot to make it easily understandable. So Canon has had RAW on their cinema cameras, or RAW video on their cinema cameras, for quite a while. It was first introduced with the C300 Mark II and the C500 way back a number of years ago. And these early RAW codec or early RAW video was weird. It's not the same as what we have today or what we're doing today. So early Canon RAW from the C300 and Mark II and C500 Mark II was recorded externally. So you can almost think of it as kind of like HDMI RAW, but not quite HDMI RAW, because if I remember correctly, it didn't actually use HDMI to carry the signal. What they did that was extremely weird to me, at least, is that they baked the log gamma that you selected on that camera into the RAW data. So it wasn't necessarily raw sensor data. It was raw in the fact that it was Bayer pattern, but it wasn't the raw sensor data compressed. It was raw sensor data that had been changed by the gamma curve that you selected on the camera, and then that was what was recorded. So that method only lasted for basically those two cameras. When the C700 came out, it still did the external RAW compression thing. It didn't have an internal RAW codec. However, they no longer baked the log gamma into the files. Instead, they had a custom, the proper term for it is an optoelectric transfer function, but it's a gamma curve. They had a custom gamma curve that was applied to the raw data off of the sensor that was then fed into the external recorder for the file. Now, the point of this whole optoelectric transfer function, in fact, the point of a gamma curve, the point of the gamma curves in JPEGs or anywhere that there's gamma curves, is to compress dynamic range. It thins out to highlight the number of values that are used in the brightest stops so that they take up fewer values, and therefore you can fit a larger dynamic range into a smaller number of bits in a file. And this is one of those things where, like I said, I really need to do a video talking about raw compression as a whole, because this is a really interesting part of that whole process. In any event, as I said, the C700, it still did external recording, but it no longer used the Canon log gamma. It used a custom gamma that was optimized to squish the sensor's dynamic range into the dynamic range that was supported by the files. Now, we don't use that either. I mean, unless you have a C700, obviously, but Canon moved on again. So Canon's current cameras, at least as of early 2023 or late 2022, use Canon's Cinema Raw Lite codec. And the codec, the Cinema Raw Lite thing, changes things up again. So this is used on, obviously, the R5, the R3, the R5C, the C70, the C200, which was actually the first camera to introduce Cinema Raw Lite, the C300 Mark III, and the C500 Mark II. So basically, all of Canon's cinema cameras and all of their hybrid cameras that support RAW video are using the Canon Cinema Raw Lite codec. Fundamentally, this starts off the same way as what the C700 was doing. So as far as I can tell, based on the cameras that Canon has published datasheets for, or white papers for, there is a optoelectric transfer function in the camera that is compressing the wide dynamic range of the sensor into the 10 to 12 bits that the RAW files use. So for example, the C300 Mark III is capable of recording a 16-stop dynamic range with the dual ISO readout, or whatever they call it. That doesn't fit if you've ever looked into like linear RAW or essentially linear RAW files, or exposed to the right. This is a big place that most still photographers come into this. That doesn't fit in 10 to 12 bits. To fit 16 bits in a linear file, in a linear RAW file, you need or 16 stops, you need 16 bits. But if you apply an optoelectric transfer function, essentially a gamma curve, you can thin out the highlight values, you can compress that into a smaller amount of bits, because the brightest stops that have all of this information that seems like it would be a good thing, it's not necessarily all useful, and therefore you can thin things out. And this is one of those big things that I really need to talk about as in the whole RAW process in a separate video. In any event, Canon's still using an optoelectric transfer function to compress the camera's sensor dynamic range into the 10 to 12 bits of the RAW file. However, they do not use the log gamma that you select. It is a specifically optimized transfer function for the camera and sensor that you are shooting on. So it's going to be different in an R5 or R5C than it is from, say, a C300 or a C500 or a C70, or, well, the C70 should use the same one as the C300 because they're the same sensor. But this R3 or the C200, for example. That file that information is then fed into the Canon CRX codec. So this is the compression codec that is used for the lossy CR3 files when you shoot stills using CRAW. This is not the first time, if you're thinking, that a still file compression algorithm or a video compression algorithm has been used for the other format. MJPEG, which many people complained about because the Canon 5D Mark IV used that when shooting in 4K, is JPEG, the still image format in a motion picture container. The HEIF, high efficiency image file format that Canon uses for the HDR images on the R5 and so forth, as well as Apple having jumped on that one as the sort of main image format for their like iPhone cameras. That is a still version of HEVC, the video compression algorithm. So HEIF is essentially, if you shoot all-eye video in a Canon camera where you would be using HEVC, an HEIF file is that, but just for one frame. So using the CRX codec in both places does make a lot of sense. Now, this may also explain some of the problems that people have seen. For example, there was a video that went around recently where a cinematographer was comparing the quality of XF-AVC versus Canon Raw Lite or Cinema Raw Lite on the C300 Mark III, which is one of the few places where you can actually shoot RAW at 4K and XF or MP4 or AVC or HEVC at 4K, so you have everything at the same resolution, and therefore you can make a better subjective comparison, although you still can't make an objective comparison because it's not the same exact frames. But he was talking about how, and one of the things he noticed was shadow detail was worse on the raw files that he had. And that's one of the problems that many still photographers have found in CRE3 files. If you start pushing them, that shadows sort of fall apart. They don't retain detail the way that the regular lossy or lossless raw still images do, which, by the way, if you are not if you're a Canon shooter and you didn't know this, or you're not a Canon shooter, or you're new to the platform, Canon does not have a uncompressed RAW format. You have a choice between lossless compression, which just makes the files smaller, but they're bit-perfect recreations of the original data, and lossy compression, that's when you turn CRAW on, where information is thrown away to make the file smaller based on various psychovisual standards and so forth. They do not have an uncompressed version, so there's no uncompressed option to talk about. So the question that all of this, as I kind of gotten a little bit off tangent there, but the question that all of this asks is what exactly is going on with the R5 and R5C when you talk about raw video? Short answer, or simple part of the answer, is both cameras use the Cinema Raw Lite codec. They do use different bit rates, which I guess is entirely possible given the way that Canon structured the codec, that they can target different bit rates. So that's a difference between the two cameras, but everything is Cinema Raw Lite. The question for me, and the one that I don't have an answer to, so I can't give you this great fulfilling answer, is what exactly is Canon doing with the optoelectric transfer function on the R5 and R5C? So the raw files are 12 bits. The sensor outputs 12 bits worth of data in dynamic range when it's shooting in video mode. Is there no optoelectric transfer function? Because there's no need for one. You don't need to compress 16 stops into 10 or 12 bits. You have 12 bits and 12 bits. Functionally, or effectively, that would just mean it's linear. And so effectively, we would have something looking at like linear raw on these cameras. Unfortunately, figuring out how to test that is a bit above my pay grade at the current moment. I have some ideas, but because it is not... I don't have open source tools available, and the reason I'm looking at open source tools, or would want open source tools, is that they make it impossible, or that it's possible to know exactly if other transformations are happening to extract information from the Canon RAW files, video files on the camera. So I can use the Canon movie raw processing or Cinema Raw processing tool to extract raw still frames from the video files. They're CRAW compressed stills. It's really no different than any other still. What I don't know is if any processing is being done between the video and still side of things, or if, as it could possibly be, that we do really have a completely linear path in the R5 and R5C. So this would be a little bit different than pretty much everything else that Canon, any of the other Canon cinema cameras at least, where you can shoot video, raw light video or raw video, and then extract. You have an entirely linear process through the whole thing. So sensor, no transformation to the raw data other than compression. Then if you extract a frame through the EOS Cinema processing tool, you get essentially the compressed data that's no different than if you shot it raw still. I don't have an answer to that yet. Looking into this is certainly on my to-do list. If you're interested in that, let me know, leave a comment. It will help me prioritize what content I put in, or I'm putting effort into or research into, in what order, if it's more or less popular or interesting to people. The final thing I want to talk about in this video is raw light compression ratios. This is a little bit of an exercise in silliness to a small extent, simply because the compression ratio doesn't tell you the whole story, but it is useful if you are looking at how much you are compressing things. So in terms of file sizes. So I did the math. Now all of this math is based on the numbers that Canon publishes. The reason I haven't done test files and so forth is because we're talking about compression, we're talking about lossy compression at that, and that makes it quite a bit more challenging to shoot content and know that you're hitting target bit rates. content that's very simple to compress. So for example, this video with a lot of black, solid black in it, will compress more even for the same target bitrate and quality than the content that is more complicated, has more detail or more fine detail in it. As far as I can tell, I should also note that all of these codecs are variable bitrate codecs. So the Cinema Raw Lite and the Canon C-Raw still image compression, there's a target bitrate, but the compression is going to vary based on the complexity of the image while still trying to get in the ballpark of the target bitrate. So it's not a constant bitrate where you can say that regardless of what the subject matter is, it's still going to be 2.4 gigabits per second. That will vary. How much that varies, I don't know. So it would require a tremendous amount of data to sort of expand on and test. So I'm just going with what Canon has published. So for the raw light codec on the R5C, the option, or the three options, are HQ, ST, and LT, and these correspond to HQ gives you about a 3.4 or 3.1 to 1 compression range. It's actually the only option on the camera where I see a change in compression looking at the numbers that Canon provides. ST, which is the first codec that can do 8K, gives you 6.4 to 1 compression, and LT gives you 10 to 1 compression. Now on the R5, so the regular R5, not the R5C, we have two levels, RAW and RAW Lite. Now this is something I found very interesting. And of course I talked earlier about how Canon still people and video people chose different bit rates. This is actually should be directly comparable, because they both implement the Canon Raw Lite, Cinema Raw Lite compression, so the technical side of the compression should be the same. The difference between the two cameras is going to be target bit rates. On the R5, in raw video mode, you have a compression ratio between 3.9 and 4.9 to 1. Now, bear in mind that this is for shooting 8K, and when you are shooting 8K on an R5C, you're shooting at 6.4 to 1. So the quality should actually be better on R5 and the R5 shooting at 8K than the R5C. Lower compression ratio means there's a higher bit rate, which means if the codec is the same, should mean that the quality's better. Our raw light on the R5 is 7.5 to 1. So it's actually like halfway between, or less than halfway. It's closer to higher quality, actually, on the higher quality end of the ST to LT distinction for the R5C. Now, finally, if you're interested, and just for sake of comparison, C-Raw still images are around 3.4 to 1 in terms of compression ratio. This is assuming a 14-bit file. Obviously, C-Raw files can be shot at 12, 13, or 14-bit, depending on whether you have the you're using the electronic shutter, or you're using continuous high plus with a compatible lens. So the electronic shutter will force it to 12-bit, same as all of the video. Continuous high plus with a compatible lens and the first curtain electronic shutter will force it to 13 bits. Or if you were shooting just electronic shutter, mechanical shutter in the normal drive modes, you get full 14 bits on the files. So 3.4 to 1. So the question that prompted me to ask was, how does that compare compared to sort of the rest of the industry? The answer is, it's hard to tell, really. So Blackmagic Design, if you look at, for example, the Ursa Pro 12K, they offer 3 to 1, 5 to 1, 8 to 1, 12 to 1, and 18 to 1 options. ProRes, which is what Nikon is using, ProRes RAW on the Z9, offers an HQ and high quality and standard compression modes. And unfortunately, Red, ARRI, and Sony don't really talk about compression, at least in the the document stuff, the specs that I could easily find on their website. So they don't have compression ratios or anything like that. Now, obviously, Red has RAW. I think ARRI has ARRI RAW. And I'm sure Sony has something RAW on like the Venice. But I couldn't find any information on it, so I can't really talk about that. So obviously, Canon's Raw Lite falls somewhere in the middle of the range for Blackmagic, what Blackmagic Design offers. Now, the R5 and R5C are a little bit hamstrung in that the Blackmagic Ursa 12K Pro can do 8K or 12K at 3:1 compression, and the R5 and R5C can only do it at about 4:1 or 5 to 6.5 to 1 or something in that range. So it's not going to be quite, it's not quite as capable. The Canon platform isn't quite as capable. ProRes is an interesting challenge because in the ProRes Raw white paper, Apple doesn't actually talk about bit rates or target bit rates for ProRes Raw. What they simply say is that it falls between ProRes this and ProRes that. So you're kind of left with some guessing. So if you're a megabit per second person and not a compression range person, to put some perspective on this, Canon Raw Lite ST on the R5C, so this is the best compression and the best quality raw compression the R5C can do in 8K, is 6.4:1, works out to be about 1,580 megabits at 24 frames per second. Blackmagic's 5:1 Raw works out at 8K at 24 frames per second. In fact, all of these will be at 24 frames per second. Works out to be about 2.1 gigabits per second, 2,164 megabits per second. Blackmagic's 8:1 compression is 1,288 megabits per second. ProRes, if you do the math, vaguely falls somewhere between 1.8 and 2.8 to 1, or 4525 to 3017 megabits per second for high quality ProRes Raw HQ. And then for the standard quality ProRes Raw, it's somewhere between 2.8 and 4.2 to 1, or 3017 to 2011 megabits per second. So the Canon Raw Lite is not the best, it's not the worst, and arguably I would say, at least as it's implemented on the R5C, it's kind of in the bottom half of the thing. It would be possibly better if it was higher. Of course, Raw on the R5 is a 2400 megabits per second, which puts it up in the higher end of the chart. Now, that said, I want to draw or make a caution on this whole thing where we're talking about. So this is part of the reason I talked about comparing video files at the start. This is very difficult to talk about objectively because we can't compare identical files. There's no way for me to shoot ProRes Raw, Blackmagic Raw, Arri Raw, Red Raw, and Canon Raw Lite in one camera at one shot at one time so that I could make a comparative assessment between all of the different compression algorithms. The second problem, of course, is that they're all using different compression algorithms. So that is going to matter because when we're talking about compression ratios, what we're talking about is the ratio of an uncompressed file to the compressed file. So the uncompressed file, if the uncompressed file is 10 megabits and the compressed file is 1 megabit, you have a 10:1 compression ratio. Different compression algorithms are going to be more or less efficient at using the bits that they have. And this is something that I don't think anybody has really good information on right now. So how sophisticated is Canon's compression algorithm compared to Arri's or Blackmagic's or Red's or whatever? The more sophisticated the compression algorithm, obviously the more computationally intensive it's going to be to do the compression, but the smaller the files are going to be, or the higher the quality is going to be for the same size file. So, and we can of course see this in, for example, general purpose video compression algorithms. So AVC, HEVC, VP9, AV1, this is the stuff that YouTube and Google and Netflix and all of these companies are distributing in. It's the stuff that we're recording in some cases, AVC and HEVC. It's the stuff we work in and day out, at least on the lower end of things. These are algorithms that have a ton of resources invested in them to make them small and efficient. and not necessarily are small and size efficient at image quality, but not necessarily computationally efficient. When you have an entire industry that is, for example, YouTube, Netflix, etc., that is everybody is using HEVC or AV1 or whatever, there's enough use that it's something that hardware manufacturers, Intel, AMD, NVIDIA, etc., are going to include hardware, specialized hardware to decode and encode very efficiently, and therefore, it can afford to trade computational complexity because you know that there's going to be hardware to do that for making files smaller at the same quality. The other hand, we have RAW that's being done by individual camera companies, and it's being done essentially individually. Yes, ProRes is an Apple initiative, but even in that case, you still don't have the economic drive to push ProRes development the same way that, say, AV1 development is pushed. So what that means is that the compression algorithms are not necessarily, well, first of all, the compression algorithms don't even have the same economic basis. When we talk about what is important in a RAW file on a computer or a RAW file from a camera versus a compressed file that you're distributing as YouTube, YouTube wants the file to be very small and still look good. On the camera side of things, I want absolute quality, and the only real consideration that I have as a cinematographer for a bit rate is if I can actually write it to a card. So obviously, like R5 can't have a 6 gigabit per second RAW format simply because there isn't enough bandwidth on a CF Express card for it to write that out. But this also makes it very difficult to objectively, or even subjectively, or even, well, I should say objectively. This also makes it very difficult to back of the envelope compare the general mainstream compression algorithms with the raw compression algorithms. So we can talk about compression ratios, but how does that actually play out? There's a lot more time and money and effort in being invested into, say, or that was been invested into, say, HEVC compared to what is invested in by Canon in the CRX algorithm and Cinema Raw Lite. Now, obviously, Canon doesn't want to make it crap, but they can essentially trade bitrate. Instead of it being very efficient, well, we'll just throw more bits at it to get the quality where we want or need it to be. Something else to bear in mind when you're talking about comparing raw compressed video and the traditional Chroma Luma Luma or YCC compressed video or video formats is the amount of data it has to deal with. RAW is incredibly efficient at storing image data. Of course, it needs to be the data needs to be reconstructed into a format that we can see. So it has to, that's usable. So it has to have the statistical reconstruction to turn a flat grid of red, green, and blue single color pixel sites into 3-color red, green, blue, or Luma, Chroma pixels. But when it comes to actually storing that initial data off of the camera, there are huge efficiency gains for working in a Bayer pattern or modified Bayer pattern in RAW. The gain is somewhere between 33 and 66% less information in a Bayer pattern of the same resolution than a chroma subsampled YCC type file or Luma chroma file. So just to quickly kind of talk about this, in RAW, you have one resolution, sensor resolution, or frame resolution worth of information, and that's all you have to deal with. Now, obviously, to make that displayable, it has to be debayered and it has to be processed and so forth, which is why it's not a good distribution option. But from a camera recording perspective, it's a great option in terms of what the sensor arrangement is. You can just simply start there. One Each frame has one resolution of worth of information that they hold. Now, when you talk about YCC or even RGB files, then you start having to talk about multiple times the resolution because you have multiple color channels. So in the worst case, 444 chroma subsampled YCC or even RGB, you're talking about 3 resolutions or 3 times the resolution of the file worth of information, because you need to have, in the case of video, a full resolution luminance channel and 2 full resolution chrominance channels for the 2 chroma components. In RGB, you have full resolution red, green, and blue. Conversely, if you're talking about sort of what is the end result typically 420 chroma subsampled YCC content, you're talking about a 1.5 resolution. So you need a full resolution chroma or luma channel, whatever that ends up being, and then you have 2 quarter resolution chrominance channels. The sum of that is 1.5 times the resolution of the video. Whereas again, with RAW, it's only 1. There's no extra information. So this also means that your raw compression algorithms that Canon and company etc. are implementing don't necessarily have to be as efficient, because they already gain efficiency from the fact that the information that they're storing is smaller. There's less information to store compared to the YCC formats like HEVC or YCC files like HEVC or whatnot. Okay, so this has been a bit of a rambly discussion, and I apologize. There isn't a great narrative when it comes to RAW, and there's a lot of stuff that I'm sure raise even more questions. There's certainly a lot of stuff that I really want to get into a lot more detail with, specifically chroma subsampling, what and why and how it works, what it's doing, and so forth, as well as talking about the actual, what the whole process is for raw compression. I'd like to talk about in a video the whole point of an optoelectric transfer function and transfer functions in general, because this is something that I think generally gets misunderstood, or it's partially explained as being like, well, we don't see things linearly, so you have a transfer function. That's part of it, but there's more to it than that. If this kind of stuff sounds like it might be interesting to you and you're not subscribed, please consider subscribing. If you found this video useful or at least informative, let me know by hitting that like button. And as always, thanks for watching, and I'll see you next time.